Good morning. Happy Monday to all. It's October 21st, and you're tuned into our continuing SIMS webinar series. It's part of our overall outreach where we take our consulting expertise in process safety and risk management that we apply to both offshore and onshore facilities and encapsulate it in the form of several webinars. And in fact, my computer is interrupting my presentation to tell me that it's time to start, so excuse me for a second. Okay, good. I got to disable that thing. All right, so a couple of logistical items before we start. First of all, I should have said my name. My name is Steve Marr. Again, welcome to our SIMS webinar series. It's being broadcast over a mechanism called WebEx, and what that means is we use it a lot for doing fine-tuning HAZOP studies, doing a lot of long-distance support. It allows very good interactive two-way communication between one, two, or even multiple parties. We're using it in a one-way mode today, so we've got all the participants on mute. We do that so you can continue your normal office activities, shuffle papers, have meetings, answer phones, etc., without interrupting all the other participants in our webinar this morning. You should be hearing my voice over your speakers on your computer. My image, we've got two images on the computer. One's our presentation, and that's being emulated as part of a PowerPoint. The other is a smaller window with the speaker. That's me, Steve Marr. It's in your upper right-hand corner. You can move it, resize it, treat it the way you'd want to for any Windows application on your computer. If you do have any technical difficulties today, please feel free to call our office, 877-532-0806, and somebody will try to work with you to get any bugs straightened out. We're going to go through a presentation, and at the very end, we'll open up for question answer. Our producer, Solveig Sather, who goes by the acronym on your screen, RMP Corp. It's RMP CORP. She'll be glad to take any questions via chat window, or if you're having technical difficulties or you need to interrupt during the presentation, feel free to send her a quick message. If you'd like to start a dialogue or interject a question directly, at the very end during the question and answer period, we'll go ahead and open it up, and we'll put you on speaker, and you can go ahead and address other participants too, and make this as interactive as all the participants want to. This is a dry run for me. This is an opportunity. I'll be speaking at the Prevention First Conference. It's an offshore facility safety conference in Long Beach, California tomorrow. And what I'm doing is I've got a very limited time on podium, and I wanted to do a dry run and also share some of the information that we'll be discussing, especially on these high-end systems, HIPS and SIS, that a lot of people are struggling with, and in a lot of cases over-apply and spend a lot more money than they want to. So that's the key topic. I'm also going to start my timer so I can kind of gauge my progress. And again, we'll be focusing on the evolution of these high pedigree safety systems and what kind of tools you can use to define the integrity level or the reliability and architecture that you need to achieve the desired level of safety for those systems. The key topics we'll be looking at is the evolution of various regulatory requirements, so you can see how these analysis tools and safety systems fit into the overall SIMS framework. We're going to quickly look at hazards analysis SIMS requirements, key design guidelines for these high pedigree safety systems, and also how protection systems have evolved and how it interfaces with other analytical techniques so you can put things in perspective. I've also got a couple slides for your reference only on other resources and things that can help you make effective decisions and do what you need to do as part of your job. So let's talk first about why we're here in general. Why do we have safety systems and safety programs in the first place? Let's look at offshore facilities and how various safety management systems regulatory requirements have evolved. First of all, there have been a lot of tragedies that remind us of why these programs exist. It also emphasizes the importance of our jobs as safety professionals. Accidents have happened. They've driven industry and agency response, both from a programmatic perspective and also from a design guideline and safety systems evolution perspective. When you look at all these major accidents, they've caused significant loss of life and property, as well as other related costs. They've had relatively simple precursors in many cases, and in a lot of cases, in all cases, the root cause was a failure to maintain its design intent. There was a design basis for what that system was going to do, and somehow, either through not identifying hazards, mechanical integrity problems, or other issues, the design intent was not maintained. So when you dig down to these root causes, it's really safety culture and management systems that were your key solution to these. When you look, what I think is very interesting, and actually I've been involved in this business since the Bhopal event in the early 80s, and I was part of the technical steering committee on the Center for Chemical Process Safety that responded to that. But it's really interesting to me when you look on a timeline for the overall evolution of all these safety management systems. When you look at onshore facilities after the Bhopal tragedy in 1984, the Center for Chemical Process Safety was formed, and industry had a really good initial response. And one of the first things we developed was guidelines on technical management of these safety systems. The API put out recommended practice 750. The regulators came on board with process safety management that you're all familiar with, but it was a real hard emphasis on onshore facilities. And it was a really good response, first by industry and then by agencies in terms of addressing this. When you look at offshore facilities, a key catalyst was the Piper Alpha accident. Industry also was trying to address how do you look at some of these high-end safety systems. I'll talk to you more about the platform safety shutdowns system study that we did in 1989. But SEMP, API recommended practice 75, early concepts for SEMS, all those came about focused on onshore facilities in the United States. In parallel, because Piper Alpha was in UK waters, the United Kingdom came up with safety cases. And a key element of that was also safety management systems. So when you look at both onshore and offshore, domestic and international, domestic being, I'm in the United States right now for people in the United States, a lot of the where it happened, when it happened, triggered the kind of response that you got both to address onshore and offshore facilities. So where are we at right now? What we've got is Safety Environmental Management Systems, or SEMS program, that's been promulgated by BSEE, previously BOEMRE, and it includes a lot of the same technical management or safety management system elements that have existed since the mid-'80s when the CCPS first put out its technical management guidelines. Safety and environmental information, hazards analysis, management of change, operating procedures have all been a fundamental platform for addressing safety management systems. In fact, the items in red, hazards analysis, MOC, operating procedures, and mechanical integrity, were things that have been recognized as very important elements, also things that get folks into a lot of trouble, and was a core part of the initial regulation that was taking the more important elements from SEMP and an early version of SEMS before the recent promulgation in 2010. Also in orange, contractors, employee participation, and auditing are things that are still evolving with respect to these SEMS programs. SEMS 2 is on the near horizon, and it's going to put a lot more emphasis on these three elements, and that's why I put it in orange. Not a requirement yet, or at least not the last time I checked the BSEE website, which was within the past 48 hours, but it is something that's on the near horizon for taking care of. So a fundamental element of all these safety management systems has always been hazards analysis. That's a key element of SEMS, process safety management, risk management programs, safety cases. All those realize that you have to identify your hazards if you're trying to control them. So let's quickly review the SEMS hazards analysis requirements. I'm providing this primarily for reference. I just want you to, because I'll be linking to this in terms of establishing an effective program as we go through our presentation. Okay, good. Some general clarifications. Something to keep in mind is there's two general types of hazards analysis requirements: a facility level hazards analysis, which most people address with classic techniques such as what-if checklist and HAZOP studies, and also a job safety analysis, which a lot of people address prior to the start of a specific operation, but is more task-oriented. We'll be focusing mostly on facility-level hazards analysis for our discussion today. And also what we're trying to do is show how you can blend some of the tools, even the ones that address the high-order safety systems, into your program so you can easily keep it up to date for all the periodic update requirements that you've got to do at 3-year intervals for your SIMS program. Another thing to keep in mind that these facility level hazards analysis techniques must be appropriate to the complexity of the operation and must identify, evaluate, and manage the hazards involved in the operation. The reason why I read through that quotation from the regs is what we're going to be doing is looking at various tools that are designed to address high-end safety systems that sometimes you don't get the full flavor or understanding from the classic qualitative techniques such as HAZOP and what-if checklist. The hazards analysis has to look at hazards, previous incidents, human factors issues. All those things are part of the framework that we're going to be talking about that you can use to evaluate the high-end systems. Whereas the facility level hazards analysis focuses on a team approach, a lot of these things, these supplemental analysis activities, can fold into that team activity and also may require supplemental analysis. So we've discussed these various SIMS requirements that provide that hazards analysis framework. Let's take a quick look at a couple of key design guidelines. Some of the ones that you'll want to be familiar with for the evaluation of higher order safety systems, well, just safety systems in general, are API recommended practice 14C and 14J. 14C, most of you are familiar with the fact that it provides reference points, examples, analysis techniques, and ways that you can look at, use your process flow diagrams, P&IDs, and translate that into making sure that you've got the appropriate level of safety. It references recommended practice 14J that gets more into the tools and how you apply those the analysis tools to your the analysis activities that are displayed and detailed in 14C. 14C has been around since the 80s, and it's been updated. I think we're in the 7th edition right now. It's been updated many times to provide that framework for hazards analysis. As safety systems have evolved and we're more into electronic systems and very high-end, high-reliability systems, industry realized that there was a need for other standards to help address those particular items. IEC 61508 and 511 are two key things that you want to be familiar with. 61508 provides a framework for identifying hazards, identifying reliability targets, how you set up acceptable risk levels, etc., and defines something called a safety integrity level. SIL, SIL, or safety integrity level, is a key measure of the effectiveness of a safety system. It's a measure of reliability and also architecture, which are fundamental aspects of how that safety system functions and how it will do its job. Functional safety, safety instrument systems for the process industry sector was promulgated or put together later on, 61511, and its focus was on safety instrumented systems. A lot of you guys know it as HIP systems. These are things that have higher end electronics, higher end logic solvers. They're trying to do more. They're trying to put more intelligence into your safety system to improve reliability, to improve effectiveness. Its primary applicability for the process industries, and key elements are identifying requirements, application guidelines, and SIL determination. One of the key things that's also mentioned in this, even though it's a standard that's primarily designed to help people who are designing and evaluating these kind of safety systems, but they also stress that I'm going to read a quotation here, the SIS management system should define how an owner-operator intends to assess, design, engineer, verify, install, commission, validate, operate, maintain, and continuously improve their safety instrumented system. There's always a recognition that the management system, the safety management system that you apply is critical, and even in terms of the design guidelines. So that link is what I'm trying to help fortify as we proceed this morning. So we discussed the general hazards analysis requirements. We've discussed general design guidelines. The design guidelines are very helpful, but let's take a look at understand a little bit better on the evolution of these protection systems and also interface with other safety management systems and analysis techniques. What we're trying to do in all these cases, the SIMS program, hazards analysis, designing safety systems, is really taking an unacceptable level of risk, which you want to measure with as a function of frequency and severity. Obviously, something of a high frequency may not be all that important if it's a low severity. Something of a high severity may not be all that important if it's a low frequency. I think I got those right. So putting those together, you really get an understanding of importance and can feed that back into, is your safety system adequate, the levels of protection, the various safety systems that apply to the scenarios you're looking at, or are you doing too much? I've seen a lot of cases where people are over-applying very high-end, very expensive safety systems in the design phase, and not only does it make the design and installation more expensive, but a lot of times the engineering contractors pulling this together aren't thinking about all the work that's involved by operations staff and maintenance to keep these things going, to test them properly, etc. So just to put a perspective, that same balance of severity and frequency is something that you often see in a risk ranking matrix. I put this up just as a reference point, and also hopefully a link to familiarity for a lot of you. When you look at the evolutionary history of safety systems, the past couple of decades have been an exciting time in terms of the design mode and where these systems have gone. A couple of decades ago, we had primarily analog devices, single element, single function, also pretty easy to understand. And as electronics progressed, you've seen a lot of evolution in terms of signal processing, application of voting logic, and right now a lot of feedback loops that go from the end device back into the logic solver to help it understand if those end devices are working properly. Well, along with that evolution in hardware, we've also had to have an evolution in how we look at whether these things are effective, basically your analysis techniques. 14C, as I mentioned, has been around for a while, a really cornerstone document that has provided a lot of good guidance and really has bumped up the level of safety for the offshore industry and other industries that may have applied it, and been a super help. First edition came out in 1986. Since then, the evolution of architecture has changed, and also with that change, a lot of people have been wondering how to fly it. I was fortunate enough in 1989 to be part of an offshore process safety shutdown system effectiveness study where we were looking at a lot of what were new technologies at the time and trying to put into perspective for three levels of platform. A level 3 system in Stratfjord, and Solveig will probably correct me on my pronunciation later. Level 2 facility in the Gulf of Mexico, and also level 1 offshore Nigeria. We looked at the application of these devices, where it made sense, where it didn't, and all these things are continuing to evolve because people have to make those decisions. How much do I invest in these safety systems? Well, a lot of that answer is, what is your target pedigree? What do you want to achieve? And SIL levels, safety integrity levels that I defined earlier, are a measure of that effectiveness. As these things have evolved, so has their reliability and architecture to help that effectiveness. SIL 1, SIL 2, SIL 3 being the most complex and reliable type of system for providing the degree of safety that you want. One of the things to keep in mind is that even though there's these high-end safety systems, and there's been a lot of evolution over the past couple of decades, and one of the nice things is in recent years, the advent of a lot of consumer electronics has meant that a lot of these systems are becoming less expensive and more readily applicable to a lot of different environments and applications. But recognize that all these single analog systems, early electronics, even with a lot of the new stuff, which have voting logic and feedback on end devices, all these are part of a spectrum of safety system that is conducive towards making your facility safer. And proper application of these is what we're really talking about here. Defining a safety instrumented system, again, the whole idea is to apply diversity, redundancy, and separation to achieve the effectiveness of that system, to give you that low probability of failure on demand. You've probably heard this term a lot, PFD, that allows you to characterize how reliable that's going to be in response to the emergency or upset condition that it's designed for. The design guidelines are listed here, as I mentioned, and also I've identified safety integrity level as a measure of SIS reliability. So how do you evaluate SIM's effectiveness? One tool is layer protection analysis. Layer protection analysis was really a wonderful bridge. Part of my early career was in quantitative risk assessment, and then I've been doing HAZOP studies since 1986. LOPA is a wonderful bridge between the two. It applies quantitative techniques, but in a fairly simple order of magnitude level to give you an ability to help make decisions, most of your decisions fairly easily, without burdening you with a lot of the details of very detailed quantitative risk assessment. A key part of LOPA is understanding your scenario, just like all these hazards analysis techniques. Understanding the initiating cause, understanding how bad it is, and what they typically do, and there's a lot of ways to do layer protection analysis, but one of the more common is for a certain severity event to establish a target frequency that you don't want to exceed. For example, if an event could result in a severe injury or fatality, you don't want the frequency of events that can lead up to that to exceed a certain level. You want to keep them below a certain amount. So what they've defined is a LOPA ratio that identifies that target frequency with the actual frequency of the event that involves the likelihood of the initiating cause and the probability of failure on demand of various systems. If your likelihood of getting to that consequence is greater than that target frequency, you've got a LOPA ratio less than 1. That's typically undesirable. And the level of undesirability feeds back into additional safety systems that you want. I'm sorry if this sounds complicated. That's why we got this printed out. For those of you who are not used to dealing with probabilities or LOPA calculations, it's a little tough, but if you do it enough, you'll get used to it. Okay, so how do you use the LOPA results? A lot of them in the design process is you want to keep that LOPA ratio to be greater than 1. Well, it doesn't have to be by adding a very expensive high-end safety instrument system. That's certainly one way to do that, but you've also got, as I mentioned, as you remember that spectrum of protection features, a whole lot of off-the-shelf, tried and true analog devices, maybe even human intervention, a lot of things that contribute to not reaching that undesirable consequence. Those also come into play, and in a lot of cases, you might argue that having one very, very high-end, high-pedigree, high-reliability safety instrument system is maybe good and may achieve a design target, but if you've got a number of diverse, different types of analog protection features, people that can get involved, and a lot of other things, if you've got enough diversity, there's an argument to be made that that diversity is also a real good thing to have. Anyhow, from a design perspective, when you look at those LOPA ratios, the lower the ratio, or the more or less than 1 it is, means that you've got to have a higher end protection feature installed such that it provides you with the level of safety that you want. And that's what the SIL level is. Usually the LOPA ratio is used to calculate the SIL level for the safety instrumented system that you want to apply. Just to summarize really quick, you've got to determine if your risk targets are met. That's part of what the layer protection analysis does. It helps you identify if you need a basic process control system, a safety instrument system, or a high integrity protection system features to be added. If you're looking at several different features, as I alluded to a few minutes ago, you can compare the benefit and cost associated with those improvements, and then identify how you can most easily reach those risk targets. And again, don't forget the tried and true basic process control systems, or even off-the-shelf standard that have been around for decades protection systems. They do provide protection and shouldn't be ignored in the lieu of this new sexy safety instrumented systems that a lot of people want to apply. And again, as I mentioned before, when you start up using layer protection analysis, a lot of times it shows you that perhaps you've over-applied a lot of very high-end and very expensive systems. One of the things that I mentioned before when I was talking about the team approach, although LOPA is calculation intensive and is often done separately, it can be really good to involve that directly with the team as you're doing a HAZOP study or some other mechanism for doing a facility level hazards analysis. More often than not, it can be done fairly quickly while the team understands the scenario, and it reinforces and fortifies their understanding, and you get some really good insights because you got that team already warmed up. Now the next 2 slides, I am running a little behind on time, so the next 2 slides I am going to skip. Provided a little example. You've got the printout, and you're also welcome to call if you have any questions. What I want to leave you with is there's a significant overlap between these key risk analysis tools. LOPA, the calculation of SIL, bow tie analysis, HAZOP studies, what if. That's on purpose. That's intentional. You want to make sure that you've looked at things a couple of different ways. You don't want to totally redo things, but a little overlap is better than having gaps when it comes to safety analysis. So don't be bashful about applying some of these techniques during the course of your HAZOP study. If it's done focused, if it's facilitated by the right person, it can be very conducive towards really understanding the system and getting some good insights from it. One of the things I also want you to realize is that as offshore facilities operate in deeper waters, higher pressures, more extreme environments, we're pushing the limits on engineering and technology. And since we're pushing the limits, this requires higher pedigree safety systems to manage this increased potential for risk. As we're doing that, and we've been doing that for all this time, for decades, we've used those higher-end protection systems that provide us with an additional level of safety to push the engineering limits even further. This cycle that you see really mandates the application of the more complex design standards and all these analysis tools that I've been talking about. However, don't over-apply them. Selective application, focused application of LOPA, even QRA tools, bow tie, all those things can be good. It can also be really bad if you're getting quagmired in terms of pulling a lot of these together. So again, I want to leave you with the fact that there's, just like if you were doing a project around your house, you got a toolbox and you'll use various tools. If you're doing hazards analysis, the core part of facility hazards analysis for SIMS is HAZOP study, what-if checklists, and also a good 14C review. But you've got a lot of other tools in that toolkit that can complement what you're trying to do with respect to SIMS and provide you with additional insights as part of that overall hazards analysis and scenario-based framework. So anyhow, I hope you got a little bit of background on LOPA today. You can see how it can fold into the overall evaluation of your systems, especially safety instrumented systems and HIPs. And I hope that you can see how it can easily fold into your overall SIMS program. What I'd like you to do right now is we're drawing this to a close, and I'm going to open it up for question and answer in just a couple of minutes. I did provide a couple of slides for you to have in your hip pocket if you need some additional background. We've been doing our SIMS webinar series since summer 2010. We've looked at things like HAZOP studies, mechanical integrity programs, safety environmental information tips, how you can pull it together effectively, regulatory issues, operating procedures, bow tie analysis, management of change, basic audit programs, how you go ahead and do audits and do them effectively. We've pulled all this stuff together that can provide a significant resource for you. And the second bullet on the list is our website that includes some background on us and also can take you to our outreach page where it provides you with recordings of these webinars. If you want to look at them, share them with folks to increase the ability of quality SIMS applications out there for industry. And also I got a couple of other good references on this page too, as well as a link to the BESI site where you can keep track of what's going on with SIMS and also the upcoming SIMS 2 requirements. And so at this point, I'll open it up for questions. And again, you're welcome to pose questions as part of your chat window to our producer, Solveig Sather. You're also welcome to ask me taken off of mute so you can interject your question directly, or if you have some additional insights, or even if you need to correct me on some things. It is morning here. and I think I'm awake. But anyhow, questions?
Just for everyone who's listening, to access the chat function, go to the little green pull-down tab at the top of your screen and select chat, which is the second box over from the right.
I guess I'm not supposed to slurp if I'm on mic, huh? Okay, so let's. So here. Oh, okay. Yeah, I forgot. We have an audience here too, and they're also welcome to ask questions. It looks like somebody's got something for me.
Okay, I have one question. How heavily does the human factor weigh in on hazards? Is it true that about 80% of accidents/incidents are due to human factors?
humans play a factor in almost everything that goes on. As I mentioned before, a lot of the root causes for these are entrenched in safety management systems. That pinwheel that you saw earlier with SEMS that included safety and environmental information, hazards analysis, operating procedures, management of change, mechanical integrity, etc., recognize that all of them, and the reason why I call it a safety management system, are all dependent on people. People during the design phase, and we do a lot of work helping the designers characterize hazard scenarios by facilitating HAZOP studies and LOPA assessments, as well as bow tie, and recently I did a CHAZOP, a control system HAZOP study for one project. But we get involved with the designers to help them to kind of flesh things out. If anybody needs more information on that, I put together a paper on design HAZOP studies that I gave at this year's April 2012's Global Congress on Process Safety. So right from the design stage, people caring, looking at things from a hazard potential, very important. Then when in the construction, again, how are they managing the implementation of the design? Then when it comes to operations, how are they operating it? Are they following procedures? Are the procedures any good? Have they done job safety analyses? Your maintenance department, do they have procedures? Is there a scheduled mechanical integrity program? Is the mechanical integrity program focused on key equipment? All these things are dependent on people. It's rare when you look at all these events that something has happened that exceeds the bounds of science or discovers a new law of physics, and that's why the accident happened. So when you go back to all these events, these awful events, awful tragedies that have occurred, at the root cause is basically somebody did something or didn't do something that they should have, but the bottom line is it still requires a safety management system as the best means of control. It's these LOPA, the hazards analyses, and everything else that are part of the toolkit that really help you understand and design a lot of these issues out of the system to fortify the level of protection there. Did I answer the question? Okay, great. Did that over answer the question?
We have a couple more questions. The first one is, if you implement HAZAD at the beginning of a design process, do you suggest any follow-up to that as the project comes to a close?
Okay, great question. Also, let me ask you, Solveig, is that design HAZOP paper downloadable off our site? We're gonna make sure it is. Okay, we're gonna double check that. But if not, within the next 48 hours, I like my paper, but I think is a real good reference point is a paper on, I called it a D-HAZOP or a design HAZOP. It's coming from a lot of the work that we do working with engineering contractors, where during the design process we'll do a high-end hazard assessment like a HAZAD. HAZAD can mean a lot of different things, by the way, but we'll do a high-end hazard assessment. We may even do a selective application of HAZOP to drill down when portions of the design need to get looked at in more detail, or you've got enough information. But we work with the designers to kind of flesh out the big issues up front. Universally, when the engineering contractors or whoever's designing the system has not called somebody in to do a look-see at the hazards, they go about on an 18-month project cycle, and at the very end of their design, they go like, ooh, we need a vessel that's triple the capacity or double the design pressure because of this unusual scenario that we just thought about, and boom, they've ordered it. It's exotic metallurgy. It's incredibly expensive, and it can't be changed. I just got through with one recently where they had to go through hurdles to go through and design some very, very high-end safety instrument systems to try to circumvent a fundamental lack of robust design pressure for a high metallurgy vessel that, if they had known about it beforehand, could have cost a fraction of the amount. So, early application of hazards analyses, like whether you want to call it a HAZAD, a high-level HAZOP study, however you want to call that, as the design progresses, fortifying that HAZOP study, filling in the blanks basically, and making that into a real good design feedback tool makes sense. And it's also it's going to be profitable. It's going to save you from lost time on your design and installation, and it's also going to save money in the long term too by fleshing out these problems early on. In the same way that you'll kind of fill in the blanks on the HAZUP study, and by the way, don't overfill in the blanks beyond your knowledge base, otherwise you're spinning your wheels and wasting your time. But as you fill in the blanks, as you get good information, in the same way you can apply other tools in your toolkit, such as LOPA, to provide additional insights and really make sure that design is focused. Okay.
We have one more question. Can you elaborate a little bit on the use of your term pedigreed systems?
Okay, good. There's a lot of different words that I use to describe two fundamental characteristics of a safety system. Fundamental characteristics of reliability. If you remember the definition of safety instrumented systems, it looked at reliability, diversity, and also a little bit of redundancy in there too. You know, are you having parallel trains? Are you using different types of technologies? So if there's a fundamental misapplication at the sub-element level, that it doesn't burn you and remove all your redundancy. So this reliability, or how, or low probability of failure on demand, or how often it's going to work correctly, is balanced out by the system architecture. Things like diversity that goes into it. It's the combination of both of those that give you an understanding of the effectiveness of your safety system. And that's really what I mean by pedigree in terms of its effectiveness. Now, again, that architecture and reliability is characterized numerically by this safety integrity level. So effectiveness and pedigree I'm using pretty much synonymously, and they're a function of reliability and also architecture of the system. And both of those characteristics go into this calculation of safety integrity level, which gives you a real measure or confidence that your system is going to work when you want it to.
I have not had any other questions come in.
All right, well, if there are any, there's a phone number on your screens, and feel free to call in, and we'll be glad to, we get questions a lot of times. Challenging questions are kind of good because it makes us think, and a lot of times it helps us understand what people are struggling with. So if you have any questions, call 877-532-0806. We have our folks all the time in the field applying these tools for the engineering contract work that we do, and we'll be glad to kind of share those. And a lot of the lessons learned and the things that have evolved over the years, we've put into papers that can hopefully provide a lot of good guidance and resources for people who are trying to put together quality SIMS programs. Anyhow, thank you for listening. And I was timing myself. I didn't do too bad, but I think I got to cut about 10% out for tomorrow. And so I'll be working on that a little bit today. And again, thanks for putting up with my dry run, and I hope this is helpful. Good day.